Good morning. All right, so we are still talking about momentum. In our last set of notes, we started talking about the law of conservation of momentum. All right, so remember that the difference between whenever we were just talking about momentum and impulse and then the law of conservation of momentum, excuse me. All right, with conservation of momentum, we're talking about whenever two or more objects are interacting with each other, meaning they are colliding with each other. So yesterday, or in our last set of notes, we talked about how you had a cue ball in pool hitting the other ball. All right, that is a collision. We had croquet balls at the end that were hitting each other. That is collision. We had two ice skaters that were facing each other and then push each other away. That even is a collision. All right, it's when two objects are interacting with each other, we know that momentum is conserved. All right, so we got our equation for the law of conservation of momentum yesterday. And even though a lot of you screamed whenever you saw it, all right, it's just M1 V1 initial. So that is the initial momentum of the first object plus M2 V2 initial. That's the initial momentum of the second object equals M1 V1 final, that's the final momentum of the first object, plus M2 V2 final, and that is the final momentum of the second object. All right, so in that equation, we saw, and yesterday, we saw that even if the objects themselves do not have the same momentum as what they started with, it's the total momentum that was conserved. All right, so today we're going to be focusing on the types of collisions. So we're still talking about the conservation of momentum, but we're focusing on the types of collisions and how momentum is conserved and what else is conserved in these collisions. All right, so we're going to be mainly focusing on three different types of collisions. All right, the first one is called a perfectly inelastic collision. All right, we're going to have elastic collisions, and then we're going to have explosive collisions. All right, and just to give you a hint, we talked about these two in our original conservation of momentum notes. Okay, so we're going to be starting with talking about perfectly inelastic collisions. All right, so these are the easiest ones to identify. All right, because you have two objects starting off, and then once they collide, they actually stick together and move as one. Okay, so after their collision, they move as one single object. All right, so we can't use our original conservation of momentum equation, all right, because that is two separate objects that are moving on their own. So instead of using that equation, we have to use this new equation. All right, so you'll see that the first part, the left side of that equation, is the same exact thing as what we have seen before. So you have the first object's initial momentum and then the second object's initial momentum. But after that collision, since they move as one, all right, we just add those masses together, and the biggest thing that you'll notice is that we have one final velocity. All right, so we don't have V1 final and V2 final like we have in the original because they're both moving as one, so we just have V final. All right, so this will be the fourth and final equation that you get on your test. All right, so if you were to pull this slideshow up and you actually played it, you will see that both of these are just very short videos. And what you see is that this object, all right, this truck is either not moving or moving very slowly. And then you have a car that comes up behind it and it crashes into it and sticks to it. So both of them move as one object together. All right, that is a perfectly inelastic collision. All right, so whenever they stick together, that is a ton of kinetic energy that is lost. All right, momentum is conserved. Momentum is conserved, but you have a ton of kinetic energy that is lost. All right, this is something called a partially inelastic collision or just a regular inelastic collision. This is what happens in the real world most of the time. All right, so most of the time you have a car hit another car and then they move together as one for a little bit, all right, but then they separate and they move separately after a little bit. All right, so again, you have this crushing and deformation like you had up here in this perfectly inelastic collision, which does lead to a loss of kinetic energy. All right, but there's also loss of momentum here, all right, because they do separate. All right, so whenever we're talking about regular inelastic collision, we have a loss of momentum and a loss of kinetic energy. So because we are focusing on the conservation of momentum, we are not going to be tested on just regular inelastic collisions. But I did want to introduce this to you because we're going to be talking about it in just a second. All right, so again, perfectly inelastic collisions are the easiest to identify because they move as one object after they collide. And while momentum is conserved, your kinetic energy is not conserved. All right, so here's our first practice problem. We have a 2.5 kilogram ball moving at 7.5 meters per second is caught by a 70 kilogram man while the man is standing on ice. All right, so in our scenario, all right, we have this man who is standing on ice. The ball, we're going to say a football, is thrown at him. Okay, now as this ball is thrown at the man, if he was just standing on regular ground, there would be friction between his feet and the ground to where he probably wouldn't move. All right, but because he's standing on ice, after he catches the ball, they will both continue to move in that original direction. All right, so I want to know how fast will the man-ball combination be moving after the ball is caught by the man. All right, so we have to look at our givens. So the ball is our first given. It's our first mass. So that's going to be our first object. So we'll say M1. So M1, the mass of the ball is 2.5 kilograms. That ball is originally moving at 7.5 meters per second. Now, I didn't give you a specific direction that it was moving at, so we always assume that it's moving in that positive direction. All right, so it is then caught by our second object, which is the man, and he has a 70 kilogram mass. Now, we know that he is standing on the ice. So because he is standing, that means that his initial velocity is going to be 0. Now, once he catches it, both of them are going to move backwards. And we want to know what will their final velocity B. So we are just looking for V final. Remember, we don't have a V1 final or a V2 final because they are moving together as one. All right, so we know that momentum is conserved, but we have a new kind of tweak to the conservation of momentum equation because they are stuck together. All right, so the first part, M1 V1 initial plus M2 V2 initial, is going to be the exact same as it always has been. All right, but now because they are stuck together, we add their two masses together and multiply by V final. Now, for me, I am always going to look for things that are going to cross out before I start rearranging. All right, it just makes it that much easier. All right, now we know that the man was not moving at the beginning, so V2 initial is 0, which makes this whole part 0. So our simplified equation is M1 V1 initial is equal to M1 plus M2 times V final. All right, now we can't cross anything out, so now we start to rearrange our equation. Well, we're trying to solve for V final, so we need to get rid of M1 plus M2. Well, it's being multiplied by that V final, so we're going to get rid of it by dividing it. So we divide by the whole thing. All right, so that gets rid of those. So V final is equal to M1 V1 initial divided by M1 plus M2. Now those M1s do not cancel out here. So we plug in our numbers. So we have 2.5 times 7.5 divided by 2.5 plus 70. So we add those masses together. So we multiply those, add those, then divide them. So the final velocity of both the man and the ball is going to be 0.26 meters per second. Now remember that velocity is a vector quantity, and they are traveling in the direction that the ball was originally going. So we said that the ball was going in the positive direction, so these two will also be going in the positive direction. All right, so this next practice problem has to do with, have you ever heard the term rubbernecking? All right, so rubbernecking is a term that is referring to people who, whenever there is an accident on the road, you slow down so that you can look and see what's happening with that accident. All right, so sometimes the curiosity factor at the scene of a car accident is so great that it produces secondary accidents as a result while people watch to see what's going on. So if we have an 800 kilogram sports car who has slowed down to 13 meters per second to check out an accident, and the 1,200 kilogram pickup truck behind him continues traveling at 25 meters per second, with what velocity will the two move if they lock bumpers after the rear end collision? All right, so we know that we have two different objects. So our sports car is our first one. So we have M1 is 800 kilograms and M2 is 1,200 kilograms. All right, now our first object, which is the sports car, is going to slow down to 13 meters per second while the pickup truck continues traveling at 25 meters per second. And both of them are traveling in that positive direction, we're assuming. All right, now after they collide, they are going to move together as one. And it's that final velocity that I've asked you to solve for here. All right, so we know that because they stick together, we know that momentum is conserved, but we can't use our original conservation of momentum equation. All right, so we have to use the one where they are sticking together. So M1 V1 initial plus M2 V2 initial is equal to M1 plus M2 times V final. All right, now remember that before you start rearranging, always go and look to see if anything can cancel out. All right, unfortunately, nothing can cancel out here. So you are going to have to solve each and every portion of this. So because we can't cancel anything out, let's go ahead and rearrange. Now, just like the last one, we're solving for V final. So to get rid of M1 plus M2, we do divide by them. Okay, now whenever, I don't know what happened there. All right, so it does get rid of each other over there, but a lot of people try to cross out M1 and M2 on this left side, and you simply cannot do that. All right, so our V final is going to be M1 V1 initial plus M2 V2 initial divided by the sum of the masses. All right, so we plug in those numbers. That's going to be 800 times 13 plus 1200 times 25, right? 25, yes. All over 800 plus 1200. Now, the 13 and the 25, remember they're both going in the same direction, so they're both going to be positive. All right, so we multiply those out. Let's see, that's 10,400 plus 30,000 divided by 2,000. We add those together, that's 40,400 divided by 2,000. That's going to give us a final velocity of plus 20.2 meters per second. So they're still traveling forward. They're just traveling forward together now. And if you notice, it's going slower than what that pickup truck was going in the first place because he added some mass to him. All right, so that is inelastic, perfectly inelastic collisions. Elastic collisions are what we talked about in our last set of notes whenever we talked about the cue ball hitting the other ball in pool. All right, and then whenever we had the blue or the green croquet ball hitting the blue croquet ball. All right, in elastic collisions, you have two objects to start off with. They hit each other, but then they move separately. All right, so this is during the collision. All right, so you have two individual objects initially. They collide whenever they hit, but then they separate and are moving separately at the end. All right, so they hit and then they move separately at the end. So these are in an elastic collision, both your total momentum and your total kinetic energy are conserved, all right, because you don't have that sticking together, you don't have the crushing or the deformation. All right, so for this one, you can use the original conservation of momentum equation. All right, so because you have two separate, because you have two separate objects at the beginning and two separate objects at the end, we would use our original conservation of momentum equation for this. All right, so we did lots of practice problems with this in our last set of notes. So we're not going to do that right now, but you will have practice on this in just a little bit. All right, but one thing before we move on to our last set of collisions is that in real world collisions, all right, most of them are not perfectly inelastic. All right, most of the time they might stick together for a little bit, but they will separate. So if they do stick together, they're going to be that partially inelastic. So they're going to stick together for a little bit and then separate. And then if you do have regular elastic collisions, such as the pool ball or the croquet ball or even the Newton's cradle, if you notice, you hear the clacking of the balls hitting each other. All right, so we know, thanks to our conservation of kinetic energy, all right, whenever we talked about the law of conservation of energy, we know that sound energy being given off is a form of a dissipation of energy. All right, so that sound means that the kinetic energy really isn't conserved in elastic collisions. All right, and even if so take a soccer ball or a football. All right, so if you were to kick those, they might not give off a loud sound. You do hear a little bit, but they do deform. And that deformation is also a decrease in kinetic energy. All right, so even in real world situations, momentum and kinetic energy are not going to be completely conserved. All right, now our explosive collisions are our last type of collisions. And this is actually what we did the majority of our examples on in our last set of notes. All right, so with explosive collisions, your momentum, your initial momentum is always going to be zero. All right, so think about in an explosion. All right, before this bomb explodes, it's not going to be moving. All right, so the initial momentum is going to be zero all the time. But after the explosion, you have all of these little shards, these little fragments that have their own momenta, but the moment that it explodes, all of the vectors added together are going to equal zero. The sum of all of them will equal zero. So your final momentum will also be zero. All right, so even though they are going to all be moving and they're going to have their own individual momenta, because momentum is a vector quantity, whenever you added them all together, they would all equal zero. So this happens, like if you see this right here, you have your tennis ball in the cannon. All right, we know that the ball is going to be shot this way and will have a positive momentum, while the cannon, thanks to Newton's third law of motion, will go this way. It will have a negative momentum. All right, so they will cancel out. So the final momentum will still be zero. And so that's what you see right here. We also saw this in our example the other day, or in our last set of notes, with the ice skaters. All right, so whenever the ice skaters are just sitting there and they're facing each other, they're not moving. All right, so their initial momentum is going to be zero. But as soon as they push off of each other, all right, they will have individual momenta. But if you add those two momenta together, it will give you zero. All right, so let's look at this. All right, we have a bullet of a mass of 0.65 kilograms. So that's our M1 is 0.65 kilograms. That's for the bullet, is fired from a 4-kilogram gun. That's our M2. With a speed of 500 meters per second. What is the recoil velocity of the gun? All right, so we are looking for the recoil velocity of the gun. So we know that this was a velocity for the first one, but what a lot of people miss is that the initial velocities of both the bullet and the gun were 0. So this 500, which we're going to assume is going in the positive direction, so it'll be positive 500. And the recoil velocity that we're trying to find are our final velocities. So both the initial velocity of the bullet and the initial velocity of the gun are 0 before the gun is fired. All right, so we know that we have M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. We use this original conservation of momentum equation because they're starting as two separate objects and they are ending as two separate objects. The only difference between this and elastic collisions is that both of these initial velocities are 0. So this whole first part cancels out. So our whole initial momentum is going to be 0. So it's going to be 0 equals M1 V1 final plus M2 V2 final. And it's that V2 final that we're looking for. All right, so we start to rearrange. We've already crossed out what we can cross out. So we start to rearrange. The first thing that we have to get rid of is this first part, this M1 V1 final. So it's being added, so we're going to subtract it from both sides. So it's going to be 0 minus M1 V1 final is equal to M2 V2 final. All right, so since we're still trying to solve for V2 final, it's being multiplied by M2. So to get rid of M2, we divide both sides by it. So V2 final is equal to 0 minus our M1, which is 0.65, times 500, that positive 500, divided by 4, which is the mass of the gun. All right, so we have 0 minus 0.65 times 500. That's going to give us negative 81.25 meters per second is the recoil velocity of the gun. Now, there are a couple of things that I want you to look at. So that negative is telling us that the gun is going in the opposite direction as the bullet. The bullet, remember, we assumed was going in the positive direction, and the recoil means that it's going in the opposite direction. So that's why it's negative. All right, if we know, thanks to Newton's third law of motion, that the gun and the bullet will experience the same force, all right, why is the bullet traveling at 500 meters per second after the explosion, and the gun is just traveling at 81 meters per second? Hopefully, you're saying that the bullet is such a smaller mass. All right, so it's the difference in mass that accounts for the different velocities, okay? All right, so that's our example of explosive collisions. All right, this was just a little chart. All right, so if we look at collisions, all right, so are they stuck together? Yes, that means that there has been lots of kinetic energy lost. And if they stay together, then that means that it is a perfectly inelastic collision. All right, are they completely stuck together the whole time? No. Well, are they crushed or bent? Yes, that means that it is a partially inelastic collision or just a regular inelastic collision, and that means that some kinetic energy has been lost. All right, if it has not been stuck together and if it has not been crushed or bent, that means that no kinetic energy is lost and we have an elastic collision. All right, so in both of these, all right, momentum has also been conserved. All right, so we're going to do a little bit more practice on this, but as always, if you have any questions, you know where to find me. Y'all have a great day today.